everyone. This is Professor Jeff Wilkerson at Luther College with an introduction to Exercise 20, determining the velocity of a comet from Astronomers as Observers and Experimenters, as published by Kendall Hunt. This is an introduction to this exercise in this lab book, and we'll just go into full confessional mode here. This is I've shot these in all sorts of different orders. I've shot a video introduction to every single one of the exercises and projects in this lab book, and this is the very last one that I'm doing. And the reason it's the very last one that I'm doing is I've never done this exercise with students. Most of the other exercises, there's a couple others that I haven't done with students. I've worked on them and I've played around them. I've worked through the data myself, but I haven't actually run it as a lab. And when I haven't run it as a lab, I don't always know where the issues come up, where people have questions and what's going on. And so this is one that I've not done that, and maybe I'll do that this year as we sit here and think about it. So that's my confessional, is I don't know as much detail about where students might find issues with this exercise, but I do know there's plenty of the learning outcomes that we've been working toward are embedded in this exercise, and it's a good exercise for doing that. So finding the velocity of a comet is one interesting thing, to know that velocity, but there's a geometrical thinking that goes on there, and careful work with data that has popped up again and again and again and again throughout the exercises in this textbook. So really the basic idea is to say you can identify a couple of stars out there and you can measure the distance between those stars. As I have throughout the textbook, I recommend using a digital caliper to do this work. These stars are far enough apart on these images that you can get away with using a millimeter ruler, as the text suggests in there. You could use a good quality ruler like this and do a pretty good job. But I always use digital calipers just to get a little bit more precision with the data work that I'm doing here. And if you measure the distance between these stars and you know the angular distance between these stars, then you can get an angular separation. You can get a plate scale. You can get an image size, and you can look at some of the focal length exercise that we have for this. I think reviewing the focal length magnification exercise and reviewing the proper motion of a star exercise in conjunction with this exercise would be very helpful. And so we can get an arc second per centimeter, or arc minute per centimeter, or per millimeter, or whatever, a degree per millimeter, degree per centimeter, or whatever units you want to use to say this is how far something has, this is the separation on the image, and that's the angular separation on the sky. And so you can figure out a sort of linear scale that relates a linear distance on the image to an angular distance in the sky. And that's important because here's your comet, and as your comet moves from one night to the next, you want to know how far it moved, and to say, okay, this is its angular distance across here. This is its linear distance that it moved. Use the plate scale to convert that to an angular distance, and you're going to get some angular distance in, say, degrees per hour, or whatever it is you're using right there. Arc minutes per hour, arc minutes per minute, or something along those lines, to say this is how fast the comet's moving. Arc minutes per second might be a good thing. And then you could actually go to radians per second if you want to. And one of the values of going to radians per second is that you want to know how fast this comet's actually moving across the sky, and you're going to have to remember that S equals R theta. This is our geometry that we've used a lot throughout this textbook, and that you use a lot in astronomy, is to say that an actual linear distance, S, is related to theta if theta is in radians over here. There's a factor of 57 that comes in if theta is in degrees, so you can do theta in degrees, maybe degrees per second, and recognize that there's 360 degrees, 2 pi radians per 360 degrees, or 360 degrees divided by 2 pi radians. If we multiply that, that's 1, because that's the same. We multiply that by there, the radians cancel out, and you just have degrees. And you see that this is 360 divided by about 6.3, and so that's where your 57 comes in. Just did a little quick walk through there where this is now in radians, and this is now in degrees down here. Anyway, you apply this and you say, okay, if you know how fast something's moving, if you know the angular velocity, delta theta over delta t, then you can say delta s over delta t. It gives you a linear velocity is going to be r delta theta over delta t. This sort of assumes that there's no line of sight velocity. So what you're getting is the velocity across the sky this direction. And if we wanted to fill this out completely, what we would do is to say this would also then be plus theta delta r delta t, thinking about that that way. But we're not worrying about that right now. We're just saying this is, and we get the distance. That's the distance it is to the comet. The distance is given to you in the exercise, and so you can convert an apparent angular speed to an actual linear speed, and go about thinking about how fast this comet is moving across the sky, and then ask questions about how fast is it moving relative to what the escape velocity would be from the solar system? How likely is it to stick around in the solar system? So that's what we've got, and that's the heart of the geometrical thinking. It ties in to other exercises as we've talked about earlier, but it's taking an angular measurement and turning it into a linear velocity, a linear motion. So if you know it went delta theta, it went some angle in a certain amount of time, we can use this relationship to figure out how much distance it went in that same amount of time. And distance per time is going to be the velocity that we seek, the speed that we seek, at least one component of that speed across the sky. So it introduces the idea of plate scale and being able to figure out how much motion on your plate. So there's all kinds of conversions right there, right? You're talking about a distance that you moved in your image. So you got your images right here. And you're talking about the distance that you moved in your image. And so that's some distance. That's some linear distance in, say, millimeters that you measure with your calipers. And you're converting that to an angular motion, given the conversion that you calculated over here. And then once you know the angular motion, you can convert it back to a linear motion, but an actual linear motion of the, so you got an angular motion of the comet. You got a linear motion of the image of the comet across the plate, and you can convert that to an angular motion in the sky. And then once you know an angular motion in the sky, you can convert that to a linear motion, how fast the comet's actually moving through space. In space. And so there is a series of steps that you walk through here. You find linear motion of the image on the plate, convert that to an angular motion of the comet in the sky, and then convert the angular motion of the comet in the sky to a linear motion, a velocity of the comet through space. So that's sort of the overall big picture of what you're trying to achieve here. I hope you have good luck with it. I hope you find it interesting and fun. I've enjoyed looking at it here as we've talked about it. Maybe I'll do it with my students this fall. Good luck with it, everybody. This is, as I said, the last video that we're shooting. It's been fun for you. Don't hesitate to contact me with any questions about anything you have related to the book. Thank you.